Hi, and welcome to today's lesson. It's on Pythagoras and Trigonometry. This is lesson 9 in my GCSE preparation course series, designed to help current year 10s practice the essential skills so that they're ready for taking their GCSE next year. We're going to be doing a basic recap of Pythagoras and Trigonometry, moving on to some trickier worded questions, some applied questions, and the importance of drawing diagrams later on. So, have a go at these questions while we just wait for a few people to log on. I'm not going to give you very long at these questions this time because they are all downloadable in advance from my website. You can download the materials there so that you can access it before the session, and I would recommend you have a go at these starter questions so you're ready to learn the kind of new content and also know what you struggle with if there are kind of topics that come up in the starter. So just a minute or so while we're waiting for people to log on. Have a go at these questions. Just a reminder that at any time during this session, if you've got a question, just comment in the chat box, or if you're watching this after the live session, then comment below the video and I'll get back to you as soon as possible. Right, 30 more seconds. That's about one more question. All right, should we go through these questions? I'm going to give you answers for the first three and then we'll go through the rest in a little bit more detail. So we should have got 15, 12.1 and 10. There were no units here, so you don't need to worry about units. It did want 2 decimal places, so you should technically write 15.00, 12.10 and 10.00. That was obviously testing your Pythagoras there. To find the long length, you do, for question 1 there, 9 squared plus 12 squared and then square root it. Same practice for the second question. For the third one, you were finding a shorter length, so you had to do 26 squared, take away 24 squared, and then square root it. So the longest length squared, take away one of the shortest lengths squared. Okay, let's have a look at question 2 then. So is this triangle right-angled? Now, if it was right-angled, where would the right angle be? Now, it looks like it's going to be here, but we can go off more than looks. This 10 is the longest side, and the longest side is always the hypotenuse, and the hypotenuse is always opposite the right angle. So because 10 is the longest side, that means if there was a right angle, it would be over there. So that means we should be able to do 4 squared plus 8 squared, and we should end up with 10 squared. So let's just check that. 16 plus 64, do we get 100? 16 plus 64 gives us 80, and 80 does not equal 100, so it is not right-angled, that triangle. Okay, so you're just applying Pythagoras' theorem, because if it was a right-angled triangle, Pythagoras' theorem would work. All right. I'm going to give myself a bit more room to do these stretch questions, so we're going to do them on the next page. Oh, zoomed in a bit. So there we go. So, question 1, find the vertical height of this triangle. Now, it wouldn't necessarily have that little dotted line drawn in for you for this question. It's just an equilateral triangle. But you need to know you can draw in dotted lines if they will give you an exact right angle. So we know that if that's drawn in, I can put a right angle there, and I've split this equilateral triangle into 2 right angles. We can do that in this question because we know, because it's equilateral, the point, this vertex right at the top there, is exactly halfway. So this side is going to be 3 centimetres. So we're actually going to use these 2 lengths of this triangle here to find the height. So just using Pythagoras, we've got a long side and we want to find a short side. So we're going to do the square root of 6 squared minus 3 squared. Okay, and that will give us, just type that in quickly, gives us the equivalent of 3 root 3, which in decimal version is 5.12 centimetres. Now always just check whether that makes sense. Look back at your diagram. The hypotenuse of that one was the 6. We're expecting the 6 to be the longest side because it's the hypotenuse. So double check, h 5.12, it makes sense. We wouldn't expect 7.12, for example. Okay, brilliant. The next one is similar. We've got a line down here that means we've actually split this triangle, which we don't know is right angled, but we've split it into 2 that are definitely right angled, this one and that one there. Now, when we've done that, we needed to know that we've got 5 centimetres on this side and 12 centimetres on that side. Because it's not an equilateral triangle, we couldn't assume it cut it halfway. You can see from this diagram it doesn't, but just be careful about assuming things like it cuts it halfway. So here we're going to use Pythagoras first on this triangle on the right, the one that I'm shading in red. So we're going to do the square root of 7.5 squared. Sorry, I don't remember if 5's not drawing. Minus 5 squared, and then we square root it, and we do get 7.5 squared minus 5 squared. We get 5.5901. I'm going to keep a few decimals there. I've just put those dot dot dots because I'm keeping it in my calculator for now, because this is my answer here, the 5 point something. Now we're going to look at the other triangle. So we're going to look at this bigger triangle here, okay? And we're going to try to find x. Because that's the longest side, we've got to do the square root of my answer, which was 5.5 something. Again, I've kept it in my calculator to keep all those numbers there. Squared plus 12 squared. And then it will give me the exact answer rather than rounding halfway through. So to get that on my calculator, I'm typing square root button and then answer squared plus 12 squared. And that gives me 13 point, let's go 2 decimal places, 24, and it's in centimetres. Okay, and again, just a little check, we've got 13.24, the length at the bottom was 12. So it does make sense, we need it to be bigger than 12, and it is. Okay, final answer. Now that was your basic Pythagoras recap. Okay, we're not going to do much more on the basic Pythagoras there. It's just applying the theorem and making sure we remember if we're adding or subtracting based on whether we're finding a long side or a short side. And also just make sure you check at the end, because it's very easy to get it the wrong way round if you're rushing, but make sure your hypotenuse is the longest. Okay, so today we have just done a basic Pythagoras recap. We're going to move on to some applied Pythagoras questions, so within other shapes or worded problems. We're then going to do a basic trigonometry recap, multi-step trigonometry questions, and to end with spotting whether to use Pythagoras or trigonometry in a kind of exam situation there. So a lot of content, but we're going to whiz through it. It's going to be snappy. In the future then, we've still got a lot of trigonometry to cover. We're going to also do 3D Pythagoras, 3D trigonometry, the sine and cosine rules, exact trig values, and trig graphs. Okay, so a lot more trig topics to cover, but today we're going to be focusing on those ones on the left. All right, let's be getting on with some of the applied Pythagoras questions. Have a little read of this question first and see if you can work out what we're going to do. Okay, I would suggest whenever you've got a question like this, we've got a worded part and we've got a diagram. Make sure everything we need is on the diagram. So if we have a look here, we've got a radius of 60 centimetres. So I'm going to straight away jot that onto my diagram. O is the centre, it tells us that. And then we've got a 60 here and we've got a 60 up there. Okay, so I've put in my content that I know. Angle BOD is 90. That's drawn in for us as that little square. Perfect. Calculate the perimeter of the tabletop. Now I know this is going to be in two parts. I'm going to have to work out the length BD, which is a nice straight line. I'm also going to have to work out this curved edge, okay, all around the circle. And that's going to be part of my circumference. So first off, let's look at this triangle bit and work out the straight edge. It's Pythagoras there. So we're finding the long side, so we're going to add together the other sides squared. So 60 squared plus 60 squared and then square root it. When we type that into a calculator, we get 84.85. Okay, I'm going to leave it like that for now. Now let's look at the circumference. Now we know that circumference equals pi d, okay, or 2 pi r. We've got to have that formula somewhere in our minds. So the whole circumference would be pi times the diameter. Remember, the diameter is double the radius, so 120. So it would be 120 pi, to leave it in exact form. Now, we don't want the whole circumference. We want 3/4 of it. Because if you imagine the rest of that circle there, sorry, that's a really bad diagram. If we cut it up, we've got 4 lots of 90 degrees and we want 3 of them because one of them has been left as that wedge. So we want 3/4, and you can do this, either you can just spot it or you can do 3/4 times 120 pi to do it in one go on your calculator, or divide it by 4 times by 3. Whichever way you do it, we want 3/4 of 120 pi. Now that will give us 90 pi, which when I work out as a decimal, I get 282.74. Okay, so my final answer, the perimeter, is both of those added together, and we get 367.59 centimetres to 2 decimal places. The question didn't ask, so just use your initiative, go for a sensible value, but always write down what you've rounded to. Okay, we're happy with that one. It's got a bit of circumference there and a bit of Pythagoras. Let's look at the next question. So, have a little read of this one. These questions, they tend to be tricky to spot straight away, but I really like them once they come out. So have a quick read. Okay, so we've got to work out the height of this stack of 3 pipes. Each pipe has a circular cross-section with radius 1 metre. So that's going to be our important information that we need to know from this one. We've got a radius of 1 metre, and we need to work out the height. It says ignore the thickness of the pipes. That means the outside, the circumference. We just pretend that's negligible. So this one looks tricky to start with because you think you don't know how low that top circle is sitting. How far into the other circles is it? And it can be really tricky when you're trying to spot that, thinking you don't have enough information. But I'm going to show you some little problem solving techniques where even if you don't know where you're going with a question, you can just start with. So we've got circles here. Mark in their centres. Okay, good starting point. Mark in the centres. Now what do you see has just appeared? Can we join those together? And we've got a triangle. Do we know anything about that triangle? What are the lengths of its sides? Yeah, we've got radius. So we've got this out to this, from the centre of this bottom one to its circumference is 1. The top one again is 1, 1, 1, 1, 1. So each side of our triangle is actually 2 metres long. Right, now it's an equilateral triangle, so we can't use Pythagoras on it yet, But what did we do in the starter question? Can you remember when we had an equilateral triangle? We cut it in half. So cut it, sorry, mine's slightly off centre because of the stylus there, but cut your triangle in half. Now we've got a right angle triangle. I'm going to take that triangle out so we can see it a bit clearer. Okay, we have got the length of the hypotenuse as 2 metres. Our base is 1 metre. We can now find the height. So our height there would be the square root of 2 squared minus 1 squared. So that would give us 1.732 metres. Now I'm going to leave it to 3 decimal places for now because my answer, if you read the question there, it says to 2 decimal places. So let's just leave it in our working to 3 decimal places. Now, can we see, we've worked out a bit of our shape, but we haven't worked out the whole height. We've actually got to go all the way up to here, so add our green line, and all the way down to here. Can you spot that top bit is actually just another radius? So we've just got to add another 1 for that top green line. And we've got to add another 1 for this bottom green line, because that's the same height as a radius. If I drew it down from that circle, you'd see it. So our height of our equilateral triangle plus 1 at the top and 1 at the bottom. So we're going to add 2 and we're going to get an answer of 3 and now I'm going to round it, 73 metres as asked. Okay, can you see how that one worked? So from going to something that you think you don't have enough information because you can't work out where the circles are sat, just start drawing on what you know. You've got the centres, you saw that triangle appeared, and wherever we've got a triangle like that, an equilateral one, we can make a right angle triangle, and that helps us solve all types of problems. Right, fantastic, good work. Well, that's all for Pythagoras for now. We're going to do our quick trigonometry recap. So, hopefully this labelling is really familiar to you. You've got a right angle triangle, so I'm just focusing on right angle trig today. And you've got theta, some sort of marked angle that we either know or we're trying to find out. We've got the opposite, which is opposite that angle, the hypotenuse, which is always opposite the right angle, and the adjacent, which is next to both those angles, theta and the right angle. Okay, so that's just our labelling, always our first step. Then you might do this so many different ways, the Sohcahtoa, but you've got to remember Sohcahtoa, whether you remember in triangles like this or just as a word. If you haven't spotted the triangles before, this is a super easy way to work it out, and you don't have to worry too much about your algebraic manipulation. It's just like using a speed, distance, time triangle, or a pressure or density triangle, which I'm sure you've used before. So to solve, you simply cover up what you're trying to find. So in this first example at the bottom here with the blue dot, that's covering the O, the opposite. So that's, for example, if you want to find the opposite, this triangle tells you to do sine theta times h. If you're trying to find the hypotenuse, then you do A over cos theta. Okay? You choose a triangle based on what information you have. So if you have the opposite and the hypotenuse, you're going to use sine. If you have the adjacent and the hypotenuse, you're going to use cos. If you have the opposite and the adjacent, you're going to use tan. Okay, so that's a quick choice. I'm not going to go through this in too much detail because I'm hoping you're a bit more familiar with this. There are so many videos out there to help you if you need a little bit more of a detailed going over. I've linked to some of the core bit maths videos on the last slide. Right, let's put this into practice and just do one example of each. We've got a finding a side and a finding an angle. So first off, finding a side. Always label first, okay? That's our very first step. So x at the top here is my opposite because it's opposite my angle that's not the right angle. And the 11 is my adjacent. So I've got OA and an angle. It doesn't matter that I don't actually have O. If I'm trying to find it, then it's useful for me, it's important. That tells us we're going to be doing our TOA triangle. Because I'm trying to find O, imagine covering that up. It's telling us to times them together. So remember that T stands for tan theta, not just tan, times my adjacent. So that is going to be tan 42 times by 11. And I am going to get 9.9. 9.9. 9.9 centimetres. Look back at your diagram for what that is. I've just left that to 1 decimal place there. Okay, so it's a quick recap, just showing how you use those triangles, how you find a side. Let's look at how you find an angle, because it's slightly different, it's just one more step. So here, the first thing we do is exactly the same, you label. This time we've got the hypotenuse, as that's opposite the right angle, and we've got the adjacent between the two angles there. We're trying to find our angle. We've got A and H, so that tells us it's ca, using the cos function. Because I'm trying to find the angle, that's hidden in the cos. Remember, it's actually cos theta. So that's the bit I cover up. It tells me to do A divided by H. So that actually tells you that cos theta equals A over H. Now to actually just find the angle, do you remember how we undo that, undo the cos? We do cos to the minus 1, okay, the inverse of cos. So we're actually doing cos to the minus 1 of A over H. So we still just used our triangle, A over H, but because we're finding the angle, we do cos to the minus 1 of A over H. So we're actually doing cos to the minus 1 of A, which is 16, over H, which is 24. Plug that into your calculator and you get 48.19. You'd probably round it to 1 decimal place if it's a degree. They'll ask you for it normally, but if they haven't, 1 decimal place is fine. Imagine trying to draw that with a protractor. It's just we can't really be more accurate than that. So 48.2 degrees. Okay, that was a quick recap. I'm hoping that's quite familiar to you. We're going to move on to some slightly more applied questions. If you do need a bit more practice, there are these questions here. We're not going to do these now, but if you're watching after the session has gone live, then you can pause it and go through these in your own time. So it's mixed practice using sine, cos and tan, finding sides, finding angles. Pause it now to go through the questions. I'm going to put the answers on the next slide. So answers coming up. Okay, there are your answers. Pause it to mark. All right, I hope that's helped if you needed a bit more of that basic practice. Fab. Now let's move on to some applied ones, because I think this is where we find it a little bit more tricky. So in this question, we have got an isosceles triangle, and we need to calculate its area. We need to find the height first, that's part A, and B is area. It might not say find the height. That's like a helping step. It might just say find its area. And you need to think, right, area of a triangle, what do I need? Base and height. I've got the base. I need to work out the height. So first things first, let's actually draw in the height line. So our height is going to be here. Now, because it's an isosceles triangle, that means it's symmetrical. So I know that if I draw a line straight down from the top point there, it's going to split this in half and at 90 degrees. So that tells me this is actually 7 centimetres and this is 7 centimetres. And I've created 2 right angle triangles. Okay, so it's only because it's isosceles, works with equilateral triangles as well. So we've got to find the height, which is this one here. We can't just use Pythagoras because we don't know 2 sides. We only know 1 and an angle. So that's why it's trig. Now remember, the first step is always to label. So I'm just focusing on this right hand triangle, this one here. Okay, and we're going to label first. This is our adjacent because it's next to the 20, and this is actually our opposite. We've labelled it H because it was height, so be careful you're not getting in a muddle there. That's why I use 2 pens, because I know when I'm labelling for trigonometry and when I'm labelling for something else. So I've got O and A, so that tells me I'm focusing on Toa. I'm trying to find the opposite, so cover that one up. That means we do tan theta times adjacent. So tan 20 times by our adjacent, which is 7. If I type that into my calculator, I would get 2.55. Okay, I'm going to leave that in there for now. So I'm just putting those dots to mean that it's still in my calculator as a raw answer. Now we found the height, so we've done part A. Part B, I'm just going to change my colour here so you can see, we've got to calculate the area. Now area of a triangle equals half base times height. We can do this as long as we've got the perpendicular height, so it's important to have that right angle there. Otherwise you'd have to use the sine rule for area, okay, and do it that way. But we've got enough information to do this way. So we have got half times our base. Now remember, we want the area of the whole triangle. So our base is now actually 14. And then times our height, which I'm just going to write answer into my calculator. And it's going to put that answer into it. Okay, when you plug that all in, you get an answer of 17.83 centimetres squared for your area. Okay, so again, splitting triangles up, but this time using trigonometry. Hope that's all right there. Let's try our next challenge. So I'm going to give you a few seconds, have a read of the question, see if you'd work out what your first step would be. Alright, so we've got a trapezium here. We want to find the size of angle BAD. Always just draw on exactly where that angle is. So angle BAD, we go from B to A to D, and we have gone through that angle there. So that's what we're trying to find. Now, tricky in a trapezium, but remember our number one problem solving technique is to find a right angle triangle. Now if I split this shape up by drawing a straight line across here, I've actually made a rectangle on the bottom and a right angle triangle on the top. Okay, so I've just drawn a straight line across. And we can actually find both of these angles. I know that this angle at the bottom here is going to be 90 degrees because I've just made it into my rectangle there. I've kind of drawn that line at 90 degrees, perpendicular to the side AB. So now all we've got to do is find that top angle, okay, this bit here. So we've got a right angle triangle. Let's find some information. The whole length of C to D is 6 metres, but we know that this part down here is 4 metres because that's the opposite side of my rectangle. So this bit must be 2 metres. Okay. I know the base of that triangle is also 15 metres because it's the same as the base of my trapezium there. Okay, so now I've got a right angle. I've got 2 metres, 15 metres, and I want to find the angle. It's looking like trigonometry. So let's start labelling. Again, different colour there for labelling our trig sides. We have got the opposite over here, so it's opposite the angle we want to find. We've got the adjacent as well. So that tells me again that it is TOA that we are working with. I want to find the angle, which remember is hidden in the tan, it's hidden in that trig function. Because I'm finding an angle, we have to do inverse tan. So tan to the minus 1 of, then it tells us O over A. Okay, let's plug in what we know. So we need to do tan to the minus 1 of 2 over 15. And we should get 7.59 degrees. Okay, so it's only a very tiny angle, that little one there. That's not our final answer because remember we have to add those two bits together to get the whole angle. So we need to add on 90 degrees and we will get 97, and it wanted it to one decimal place, so 0.6 degrees. That's your final answer. Okay, so we've just split it up again, drawing in perpendicular lines so that we can find a right angle. All right, well done there. Should we try challenge 3? Okay, so this one you can see it's actually been split up already for you. Have a quick read and see if you can spot the first step. Okay, have we spotted it? So we've got two triangles basically, and we're going to treat them separately. Eventually we want to work out the whole base. So we probably want to work out the base on the left and the base on the right, maybe. we could, if this whole triangle was actually a right angle, you could just use the 7 and the 12 and the 65, or even just the 7 and the 12 and use Pythagoras. But we don't know whether it is a right angle yet. We don't know what that angle C is. We don't have enough information. So use it as two different smaller right angles. Now this first one, I'm just going to straight away find this bottom length here. So I'm going to label for trig, and I'm going to label this as my hypotenuse. I'm going to label this as my adjacent, and I'm going to try and find my adjacent. So I have got A and H, I have got cos or ca. I'm trying to find the adjacent, so I need to do cos theta, which is cos 65, times my hypotenuse, which is 7, and I'm going to get 2.958. I'm going to leave it like that for now, so I've got enough in there, because it wants my answer to 3 significant figures at the end, so I've got 4 significant figures there for now. So I found this part. Okay, now I need to find the other part. Now, we don't have much information about that side of our triangle, so we actually need to find out this bit first. I'm just going to put a little X where I mean. Okay, we need to find that height of our whole big triangle. So we're going to use trigonometry again on that little shape. You could use Pythagoras now that you've got an answer, but that's relying on an answer you've just got. If that answer's wrong, then your next step is wrong, and the next step is wrong, and so on. So if possible, I would always go back to the information you've been given in the question. So now let's label how we want it. This is the opposite still. That's still the hypotenuse, so I'm still going to use that as my hypotenuse. But this time I've got O and H, so I have got so. I'm trying to find my opposite, so I need to do sine theta or sine 65 times my hypotenuse, which was 7. Okay, and sine 65 times 7 is 6.344. So I've now found that height, or x. Now that's not part of my answer yet, but I'm just going to use that to now find the length DC. Okay, so now I want to find this length, DC. I'm going to have to use Pythagoras now, using this value that I've just found for x, because I don't have the option to go back to the information in the question. And as long as you've got enough decimal places and we haven't rounded, it's still going to be nice and accurate. I'm actually going to just use that as my answer function. So DC is going to be square root of, now remember I'm finding a shorter length, so I've got to do the hypotenuse squared, take away, and I'm going to use answer squared. Okay, putting that answer in there, so it's nice and exact. And I would get 10.186. Okay, that's my length DC. I've got to add on the length I found from the previous question. So we have got to add on 2.958, and we would get 13.1 when we rounded to 3 significant figures. So it's 13.1 centimetres to 3 sig fig as our final answer. Okay, so split that one up. We've done a bit of trigonometry, then trigonometry again, and then a bit of Pythagoras to put it all together. And always check back at the question. Have you added the correct ones together? Have you got that whole length? Fantastic. Right, let's do our last challenge question for today. Challenge 4. Have a little read, see if you can spot the starting point. All right, shall we have a look? So it's made from 2 similar trapeziums. The pattern has 1 line of symmetry. So that's just showing you it's symmetrical. Just like before when we had an equilateral triangle or an isosceles triangle and we could split it down the middle. So that's going to be really important for this, the fact we've got that symmetry. Now that means, can we see at the top we've got 18 centimetres, at the bottom I've got 10. Now if I draw a line, remember you want perpendicular lines, we want to create right angles. So straight up from my 10 to the top, I can do it on both sides and it's still symmetrical. We've got that pattern. So I know that 10 centimetres was this middle bit. If the whole of the top is 18 and my shape is symmetrical, I know that must be a 4 there and a 4 there. Are we happy with how we've done that? Now you can see, hopefully, that on this left-hand side we've got a right angle triangle. I'm going to pull it out so you can see it a bit clearer. We've got a right angle triangle with a top length of 4. We've got our angle we're trying to find. Now we've got a height of 25 because it goes all the length of the shape, and we're told in our original diagram that our shape is 25 high. So we've just created that right angle triangle there to try and find x. Now I know that's trigonometry because I've got sides and an angle. So let's start labelling. We've got our opposite and we've got our adjacent, so I know it's TOA. We're trying to find the angle, which is buried in the tan. Because I'm trying to find an angle, use inverse tan of O over A. So actually let's sub that in with our values. That's inverse tan of 25 over 4, which gives us an answer of 80.9 degrees. Okay, so it's actually much simpler than the previous one. We only had to do one triangle, one case of trigonometry, rather than 3 different types. But sometimes it's tricky to spot the right angle triangle. So remember, draw in those perpendicular lines to any straight lines you've got. Make right angles. All right, super work on that. The last little bit we're going to practice is some worded questions. Now, I don't want you to actually complete these questions. All I want you to do is draw the diagram. So I'm going to do the first one for you, and then I want you to do some of the others. So let's just zoom in a little bit. So just focusing on this first one, the ladder question. So a ladder 15 metres high is placed 4 metres away from the foot of a wall. What angle is the ladder placed at to the ground? So we've got a wall and we've got a ladder going up to it, it's a nice diagonal ladder, and we've got the distance away from the wall. I know that's my right angle, okay, the ground and the wall generally at 90 degrees. So my information, the ladder is 15 metres high. That doesn't mean it's 15 metres high up the wall, it means the ladder is 15 metres long. So that's the diagonal because that's my ladder leaning against the wall. It's placed 4 metres away from the foot of the wall, so that's my 4 metres. What angle is the ladder placed at to the ground? So we want the angle between the ladder and the ground. That's this angle here. And that's what we're trying to find. Okay, so that's all I want you to do is draw those diagrams out. So make sure you've got the information of any sides, where the right angle is and where the angle is. Okay, 5 questions there. I'm going to give you 1 minute or so to see how many of those you can draw. Off you go. Okay, 30 more seconds. Remember, if you're doing this in your own time and you've paused it, take as long as you want for these questions and try answering them as well. Always good practice. Okay, let's have some answers. So the triangles are coming up. This is what your triangle should have looked like. In some cases, your triangles can look slightly different, like especially the bearings one, so about the north and the east. You could have gone east first and then north. So if we look at this bottom drawing here, your triangle could be this way up. okay, with a 6 and then a 5. Absolutely fine, as long as your diagonal is sort of ending the right place. In this case, it would be tricky because we want the bearing, and the bearing has to go from north. So if you'd found this angle, you'd then have to take it away from 90. So just be really careful if the question is talking about bearings. They go from north and they go clockwise. So that has to be your bearing. Okay, the proper answers are on there as well in case you tried the questions. So pause it if you need to mark your work. Any questions, just comment in the chat box or below the video and I'll get back to you. Right, let's end with a quick quiz on whether we're going to use trigonometry or Pythagoras. So with these questions, either shout at the screen, trigonometry or Pythagoras, or both, or write down, if you've got a little piece of paper with you, T or a P, or both. If you're thinking both, try and write what order you'd use them in as well. Okay, we're going to be quite quick with this. So it's on first glance, what information do we have? Is it Pythagoras? Is it trigonometry? Things to look out for. Pythagoras, it involves all three sides. So either you know 2 and you're finding 1, or you know 3 and you're working out whether it's a right angle. Trigonometry, angles and sides, but still has to be right angle triangle. Okay, let's have a go. First question, Pythagoras or trigonometry? Good, Pythagoras. We've got 3 sides there. It's going to be quick, did warn you. Next one, Pythagoras or trigonometry? Yep, that one's just Pythagoras, okay, just sides. Next one, Pythagoras or trigonometry? Just Pythagoras again, split it up and we've got it. This one. Trigonometry, super. We've got that angle thrown in there as well. This one. Trigonometry, super. This one. Hopefully we got Pythagoras, then trigonometry. Okay, Pythagoras to find BD, then you've got enough to do trigonometry to find CD. This one. All right, this is one we actually just did. Trigonometry and Pythagoras there, both of them. This one. Yeah, have you got Pythagoras, then Pythagoras? It's double Pythagoras one. Next one. Yeah, this is just trigonometry. Next one. Pythagoras, then trigonometry. We've got both in there. What about this one? Okay, we've got Pythagoras. This one. Trigonometry. In the question, we've got the angle 70 to 80 degrees. This one here. Trigonometry. We've got to use trigonometry to find the height of this question. And this one. Okay, Pythagoras, and last one. Super, just trigonometry. Well done. I know that was quick, but it's about spotting straight away. What are we going to use, Pythagoras or trigonometry? Right, really well done today. Followed that and kept up. The whole PowerPoint is available to download from my website, mrskslightbulbmoments.wordpress.com. That includes my annotations, all my workings. If you need further practice, there are some videos on Corbett Maths. The first few are for Pythagoras, the next lot of trigonometry. Our next lesson will be this Wednesday at 5 p.m. on the same platforms, YouTube and Facebook. And we'll be focusing on some slightly more difficult trigonometry. All right, well done today. I'll see you Wednesday.